question is there a shape that you can fill with water but cannot paint? In other words, is there a shape that would have a finite volume but not a finite surface area? For instance, if we took this cookie and made it a three-dimensional object, there would be a specific number of cookie crumbs in it, but could you cover the whole thing with icing? In other words, the question of Gabriel's horn. And we're going to use calculus to prove whether or not you can prove the surface area or the volume.
Alright, so pretty much I'm going to explain what L'Oreal was trying to prove with more of a picture. Alright, so we have this symbol of Gabriel's horn. Obviously it's not complete because it would have to go infinitely off this way. But what we have here is we have an X, Y, Z axis. You have your Z, which is running up and down. You got your X and Y, which are running perpendicular to each other. So you got a down and two crosses. So say my right arm is the X-axis, my left arm would be the Y-axis, and then my body would be the Z, creating a three-dimensional shape. And what we did was we took the graph 1 over X, and we drew it on the X-axis, okay? And then we revolved it 360 degrees around the X-axis, and then created 3D by giving it some dimension. And then the idea is, what she's trying to prove is, if we shrink this down and keep going and going until it's infinitely close to this X-axis, that will give it a finite volume, okay? But the idea is, will it have a finite surface area, or will it never be able to be painted or covered by a surface? So that's kind of what we're trying to prove with more of an image or picture.
Here we're going to try to graph Gabriel's horn. In Z2, I have selected an equation. What we did with this equation was we used common sense, and we used XY, ZY, and YZ traces to decide what the graph should look like from each side. Basically, we thought from the top it would look like a circle, and then from the other sides it should look like the graph of 1 over X, which is being revolved around it. So using this method of thinking, we came up with this graph. This is from the top of Gabriel's horn. This has a plane which is getting ready to shrink down into the horn. It's very difficult to graph 3D, and we could not get all the way to the end of the horn. But as you can see around the middle, if you trace right here around the middle, it's getting ready to go somewhere. And this is where Gabriel's horn goes down and gets infinitely close to right in the middle, which would be the Z-axis, where Z equals 0. It should be approaching it. And then in our other calculator we have this one is a look from a lot closer from the side of Gabriel's horn. This would be right at where it's starting to shrink into the horn shape. This is a different equation, actually. In this equation, we just took the equation for Gabriel's horn, a 3D equation, and we plugged it into, or we took the 2D equation and plugged it into an equation that makes it 3D by revolving it around the Z-axis. And with this, we yielded our graph. That is, we did some tweaking in the window, and we zoomed in to the very side of it to give a pretty nice view of the side of Gabriel's horn where it's zooming up close.
This is the proof of the convergence of improper integrals. We have an improper integral right here. It's 1 over x to the p power with the bounds of 1 and infinity. If you integrate this, it should come out to 1 over p minus 1, assuming that p is greater than 1. Here's the integral, which you can change it to x to the negative p power. And if you integrate it, you get x to the negative p plus 1 power over negative p plus 1 with the bounds of 1 and infinity. From here you can simplify it to 1 over p minus 1 plus 1 times the quantity x to the power p minus 1. And then you can break it apart, plug your bounds in, and solve. You have the limit as x goes to infinity of 1 over negative p plus 1 x to the power p minus 1 minus 1 over negative p plus 1. As x goes into infinity, the denominator jumps to infinity, making that value 0, and you get the value 1 over p minus 1.
Gabriel's horn is modeled by rotating f of x around the y-axis, the equation 1 over x. So to find the volume of that shape as it goes to infinity, 1 over x is your radius, so you'd square that and multiply it times pi. And when you're integrating here, what that does is that adds up all the different radiuses, so it gives you a three-dimensional value. So using the improper integral, what we learned from that, we know that it's going to be 1 with 2, so it's pi times 1, so it's pi cubic units. Surface area is a different equation, but you still use an integral to do it. You keep going and you do it off to infinity. And as you do it, since you end up with an x in the end, it goes off and it diverges to infinity. So it's not an actual number, so the surface area is infinite, but the volume is finite.
This time, this place, misused, mistake.